the kind introduction of me. Hello, everyone. I am Ramin Ghiasi, and I'm very excited to be here in ETH in chair of structural mechanical maintenance. Today, I will present a summary of what I have done during my research studies in UCD and also what I have done before in China, and some of the lessons that I got from those work on structural health monitoring and intelligent transport systems. Let's start with a quick background presentation about myself. Let me see if it works. Yeah. I got my PhD in 2019 in Iran in structural engineering, and after that I was working with Southwest University in China for around 2 years with Professor Nouri, where the research topic that I was working there was on structural health monitoring of city infrastructure such as pipeline. After that, in 2022, I moved to Ireland and I was working for around 3 years with a state lab research group in University College Dublin. And from the beginning of this year, I moved to industry, and currently I'm working in a consultant firm in Ireland as research engineer. During my academic and professional journey as researcher, educator, and industry engineer, the main research focus of my work was developing and using AI for different civil infrastructure and transportation systems. To make it more categorized, that we can divide them to four categories. One of the main one was using AI and developing system for direct and indirect monitoring of railways, tracks, and railway bridge. And we use different systems such as wayside monitoring and also the drive-by or onboard monitoring systems. I also was working on different wind energy infrastructures and different wind turbine, offshore, onshore, and floating wind turbine for health monitoring of different systems. And also I was working on industrial assets such as train wheels and also different high-rise buildings. And finally, which is mostly my current work in R&D, is on intelligence transport systems and using various type of data that we can have from IoT sensors for predicting and managing the traffic on different roads in Ireland. Let's start with the idea and the general perspective of AI. When we speak about using AI for infrastructure monitoring, we can divide it from macro scale to three main steps of data preparation, model preparations, and result extraction. For data, in most of the case, we have access to different finite element model or digital twin, and that can provide us with data. On other side, we can also have access to different sort of data that came from sensors, and sensor can be installed on the structure or can be monitoring sensor from the IoT sensor on ITS systems. When we have the data, we need to do some pre-processing and using some model based on the objective of the systems. And after that, we can have some information about the current state or future state of our systems. That three main steps can be divided to more finer steps, such as data collection, data preparation, feature engineering, and so on. I start my work in UCD with one question, that from all of this part or from all of these steps, which one has the most important impact on the insight that we can have from the system? Data or the raw data that we have, or the AI model that we are developing? Is there any priority for focusing or zoom, or we should put or focus on both parts? And then my focus become more dedicated to the link between these two, or feature engineering part, that somehow prepare data as input for different AI model. Feature engineering can be also divided to different steps and different names, such as feature extraction, selection, creation, and scaling. My second question then become that if we want to go with feature selection as one of the most important pipeline or steps in developing AI models framework, do we have any sort of easy to extractable feature that can be used for different scenario? I mean that apart from a specific domain, can we find some sort of general features that can be applicable on all domain, not just a specific domain? And that two questions somehow shaped my research project during my time in UCD and the work that I'm also currently doing. Let's start with some of the work that we have done on transport infrastructures. And mainly, the result that I bring today is mainly on two data sets that we are working on. One of them was from light railway system in USA, Pittsburgh, and the other one was the data set that was collected from the uh, uh, high-speed railway network of France in collaboration that we had with SNCF on that specific project. For the first dataset, our main goal was to somehow detecting maintenance need of the system based on acceleration response data that was recorded on onboard systems. And from that, I mean that some accelerometers that were installed on bogie and also on car body of that train. For SNCF, our objective was to detecting geometrical defect of the track and the large variety of the geometrical defects such as cant, twist, alignment, and so on. So for the first data set that is open access data set and can be accessed through the online link. The data was recorded from 42 kilometers for 4 years, and it has a large variety of data. I mean that it also had the environmental conditions and also track maintenance log. And the idea that we was trying and we implemented on this data set was to can we detect the maintenance need 2 months before actual maintenance applied on that section of the road, because as I mentioned, we had tag maintenance log, and we was trying to see any sign of needs for maintenance log from acceleration response data that was recorded using different onboard monitoring systems. And we was focusing on two specific maintenance activity, tamping and surfacing, that both of them are some maintenance activity for correcting the geometry of the track. We started with acceleration response data and raw acceleration response data, and to check different and impact of different feature set, we defined a somehow holistic approach that compare different feature extraction method, different feature selection method, and different feature classification or ML approach. For feature extraction, we create a pool of features from all domain that was can be extractable from the raw acceleration response data. I mean the time domain, time frequency domain, wavelet bucket relative energy, autoregressive model parameters, and so on. So we try to extract some to make it usable in case if we want to go for IoT devices. We try to focus on easy to extractable features. I mean that, for example, features such as mean of acceleration response data, root mean square of acceleration response data, and similar features. For the feature selection and feature classification, we also test different algorithms that can be used on such cases. The result was quite good. I mean that the results show us if we goes with the statistical features that such as root mean square or peak value of acceleration response data, we can predict the acceleration, we can detect the needs for maintenance need on that section of the railway track with around 94% accuracy. And the other domain also show us a good accuracy. Furthermore, the main thing that we figure out that if we find the good feature set, no matter what ML model we are using. I mean that in previous slide I shown you that we was working with random forest, nearest neighborhood, support vector machine, cascade for neural network, different architecture of neural network, different architecture of shallow deep learning model. But results show us if we choose or feature wisely, we can have a good result no matter what ML approach we are using. And we also did some exploratory data analysis or the EDA to see or make some make our AI model more explainable, and it was show us the features that came from the accelerometer that record in X, Y, and Z direction has more sensitivity to detecting track maintenance compared to the sensor that just record one direction of the data. We extended that work for another data set, and in a collaboration that we had with SNCF in HarmoTrack project, we had access to data that was collected for around 3 years from whole railway network of France for highest-speed train that was traveled around the whole network each 2 weeks, and it's create a very great data set. I mean that we had access to 1.8 million of data that was collected for around 3 years, and it was diverse data set. I mean that it was collected from different geometrical defects using two systems. One system was acceleration response data that was recording using the 6 sensor, and the sensor was located in head, middle, and tail of this train, and also another system that was recording track geometry defect using scanning and lasering systems, and different geometrical defects such as alignment, cross level twist was recorded in that 3 years. We defined and developed a dedicated data-driven systems for detecting the geometrical defect on that railway, and for that we once again went for a statistical time domain features. I mean that once again, Ramin square, maximum, and similar statistical feature of acceleration response data. And we also did some work for data segmentation to divide a whole railway line to different segments of healthy section and defective section based on the data that we had from track geometry device, and also based on the standard of SNCF. I mean that if the deflection of the track or if the misalignment of the track was higher than a specific threshold, we call that section as damaged sections or abnormal sections. We went for different anomaly detection algorithm, and most of them was shallow ML approach, for example, such as one support vector machine, and the result was quite acceptable. It gave us around 93% accuracy, and also we have done a set of sensitivity analysis to figure out which sensor have highest impact on performance of the system. I mean that if we go in previous study, I shown you that the sensor was installed on three locations, and in each location it was installed on both bogie and also on car body of the train. So we also did some sensitivity analysis based on the result of our algorithm, and it was showing us the bogie and transversal direction of bogie. The result that the acceleration response data that was collected on bogie has the highest impact on performance of our classification or anomaly detection algorithm for detecting the needs for and type of geometrical defect. We also extended that work to other line. I mean that in previous work, we was just focused on one specific line between two cities of the France. But the challenge become more obvious when we try to use the model that we are training on the specific railway line and want to test it on data that comes from another line. And because of distribution amalgamation between different data source, it was really hard to use the model that is trained in one railway line on another line. In this figure that show the PCA plot of data, and plus means healthy data and minus means negative data, you can see that there is no clear cluster for data of healthy sections, or clear cluster for data that came from the damaged cluster. So we went for different idea to how we can solve this challenge, and finally we went with a dedicated domain adaptation framework to find a space that can be used and find some features that can be applicable on different line, not for a specific line. And once again, we went for with time domain statistical features, and results show us if we goes with proper feature set and also proper ML algorithm, we can have up to 25% accuracy increase in defect detections using transfer learning and domain adaptations for this specific case if we want to test it on different line. And I mean here we use some source data for training our algorithm and then different target data, and here in target data means data that comes from different line of that label systems. We went also for some other steps. I mean that here in this work, we was focusing just on detecting geometrical defect, but we didn't focus on type of geometrical defect. In subsequent work, we work on how we can detect the type of geometric defect, is twist, is cant, or is misalignment, and we went for some hierarchical modeling. Generally, all those work show us that if we find a good feature set, AI model is not the most critical part, and that link between data and ML model is have this highest impact on performance of systems from the model that we can develop. We also try to check this idea on some other domains, such as bridge monitoring using drive-by approach. And we started a collaboration with my colleagues, Robert Corbally, and on those work, we first of all started with some of the data that he was recording on laboratory bridge models using toy car, using accelerometer that was installed on axle and bogie of that car, axle and car body of that car. And we also try to check it for different type of damage. I mean that for seized bearing or changing the boundary condition, and also for different crack size in middle of the beam. The framework that he was developing was somehow similar to other paper that I've shown to you. I mean that we went with raw acceleration response data and extracting some features from them, and then trying to find the most suitable features for our application, that in this case was detecting the type and the location of damage on bridge. For feature selection approach, I tested different architecture. I mean that from wrapper-based feature selection method, filter-based and hybrid model for feature selection. And for feature extraction, also we went for different domain. We try to test different combination of the optimization algorithm for selecting the features and ML algorithm for classifications and some other combination of the model to make sure that our approach is not biased to a specific algorithm or a specific ML models. And result will show us if we find the feature set and if we use good feature set, the accuracy of the system in most of the case is not very depend on type of ML model that we are using. And the thing that somehow control the accuracy is the type of feature that is using for input of the ML model. We also did some EDA analysis to see if any other insight we can get from the framework that was developed, and result will show us that if we install the sensor on axles, it give us better sensitivity for different damage. I mean that two type of damage that we was discussed is crack and seized bearing for both cases. We also went for another applications. I mean that in this case we was working with University of Porto for defective wheel untrained system in train track interaction systems, and the idea was to see if we can detect the different type of out of roadness, such as wheel flat or polygonal wear, in a specific setup of the sensor. The setup of sensor that was used in this work was mainly wayside monitoring systems. I mean that the sensor was installed on track, and the model that was used was a specific type of passenger train in Porto. And the result was shown us, and the approach that we was using was based on unsupervised feature selections, extracting time domain features from the acceleration response data that was recording using those sensors. And the result was acceptable in case of, first of all, detecting there is some defect in build, and also in classifying and somehow clustering the different severity of wheel flat on that systems. We also went for checking the sensitivity of the approach on location of the sensors. I mean that what would happen if we, instead of putting sensor on track, putting it on sleepers or near to sleepers or somewhere between two sleepers. And results was showing us that if we find a good feature set, the selection of the position of the sensor is not very critical on performance of the systems. And with simple features such as root mean square or peak value, we can have a good estimations about the state of wheel flat on train, at least in this case for this model that we was using. And we define some sort of boundary plots for different value of two selected features to somehow define some threshold for knowing the state of wheel flat. That was the works that I have done on transport infrastructures. We also try to see the boundaries of approach on different domain, and for that we was working on different type of wind energy infrastructure and different type of wind turbines. I had this chance to work with four PhD students during my time in UCT, Mahdis, Mahmoud, Theo, and Satish, and each of them looking to problem from different perspective. I mean that the general idea was to using data-driven approach for a structural health monitoring of wind turbine, but from different variant of data and different approach to the systems. I will assist part with some of the work that I have done with Satish, and in that specific project, he was developing a finite element model of offshore wind turbine, monopole offshore wind turbine, and the idea on that work was to using accelerometers for knowing the scour around the foundations and knowing the depth of the scour around the foundation. Sensor was installed on cover of the wind turbine, and 9 sensor was used, and those sensor was, as I mentioned, accelerometers, and we used raw acceleration response data as input of the framework. The framework was had some steps. One of the main steps that I focused here is the feature extraction and selection part. We went once again with statistical feature from time domain, and result was showing us if we go with selected sensors. I mean that the sensor that is closer to the transition phase, we can have a good accuracy in detecting the size and depth of a scour in this model. We also test this approach for another scenario. I mean that in series of work that Mahdis was doing on her PhD, the idea was to see if we can find a suitable feature set that can be used for blade crack detection under different environmental conditions. And the data set that she used was based on the specific data set that was collected in DTU, and that data was collected on the different speed of the wind turbine and also different environmental conditions, different loading conditions when the electromechanic shaker was hitting the blades. And we tested different approach. We developed a different approach for how we can use those data. I just brought one of the work, and the one that was mainly on how we can remove the environmental conditions from the data that we have. I mean that in that case, we went for extracting time domain, time frequency domain, and frequency domain from our acceleration response data. And the main challenge was that most of the feature was very correlated with environmental conditions such as temperatures. And idea was to how we can remove those and find the features that are also sensitive to type of damage. So based on the idea of removing and selecting the features with lowest correlation with temperature and lowest variations during the healthy condition of the blade, we developed a dedicated system, and result was showing us it can detect a state of the blade. I mean that it is healthy or is defected, and there is some sort of crack on blade with high accuracy. We also tested that approach on SHM challenge that was organized by Bedouin organizations, and on that work I was collaborated with Theo, or PhD student, and for that we was developing a framework for detecting 3 different type of events that can happen on wind turbine: icing event, aerodynamic imbalance, and pitch drive failures. We went with a similar approach, I mean that extracting time domain data and time domain features and using them as input of anomaly detection algorithm for 2 scenarios. I mean that for icing event and aerodynamic imbalance, the result was quite good. It shows more than 95% accuracy in detecting the status of the systems. For pitch drive failure, the result was not good if we use just time domain data. And we also added some new features from frequency domain and accuracy improved. In addition to that, we also test and do some sensitivity analysis to see which sensor have highest impact on performance of the or anomaly detection models. And result was shown us the main shaft, the sensor that is installed in main shaft has the highest sensitivity to different type, at least 3 different cases that we was discussing here: pitch drive, icing event, and aerodynamic imbalance. Currently, I'm working with another PhD student of our group, Mahmoud, for extending the idea of scour detections around the monopile for different wind turbine. I mean that not just one, the system have this capability to be transferable to other wind turbine in same systems, in same farm. And when we go from one wind turbine to another wind turbine in same farm, the loading condition may be changed, the soil condition may be changed, and all of this change shift the distribution of data a bit. And this can be challenging when we want to develop a generalized approach for scour detection around the foundations for whole wind farm. We test and we develop dedicated transfer learning and domain generalization approach to see if we can find a way to work with this type of data. And for this data set, the best feature set that we find is mainly the features that came from frequency domain. I mean that in this case, we cannot rely on time domain data, and time domain, statistical time domain data is not very great and using for when we want to find some sort of transferability between different wind turbine in same wind farm. We are also currently trying to extending that idea with Mahmoud for different wind farm. I mean that in previous slide I've shown that what would happen if we want to use our model for one wind farm. In this case, what would happen if we have a SHM model that is trained on data from one wind farm and want to be tested on data that came from another farm with different loading conditions, with different soil conditions, sometimes different structural conditions for the wind turbine and also different soil conditions. So all of this uncertainty shift and change the data case by case. I mean that in sometimes the data that we have from healthy condition of one farm is very similar to data that we have for a cover around, for example, 3 or 4 meters on another farm. So finding those feature set that can be used in different domain is one of the critical part of this research that is still ongoing. Let's jump to another type of work and another domain, and this work is mostly related to what I'm doing right now in R&D, but it's a start from 2 years ago when I went to Czech Republic, and there I was as a secondment. I was in transportation center, and they were using a specific type of sensors or magnetic sensor for knowing the speed of vehicles and flow and speed of vehicle in different section of the Czech Republic. The main idea was to using those magnetic sensor as some sort of alternative approach for knowing the traffic in different roads, because it was cheaper compared to CCTV camera, and also it was easier to install compared to loop detector. Those sensors the accuracy of those sensors for detecting the number of vehicles and the speed of them was good, but the classification performance of them, I mean that knowing the type of vehicle was not good, and the accuracy, as far as I remember, was around 40 or 50%. So I went for the idea of using different feature set and creating a different pool of features and return back to raw magnetic data or raw magnetic waveform that we can have, and return back to the data extraction part. We extracted around 100 features from magnetic detector, and we also used some sort of verification procedures to make sure that if we classify a vehicle as, for example, car or HGV, we also make sure that that classification is correct. And for that, we use other ITS systems, such as a specific microwave detectors. And result was showing us if we find and if we go with selected feature set, we can expect to have to 93% accuracy in detecting different class of vehicles such as car, HGV, LGV, and van. I also had a collaboration with my colleagues Amir Reza in our school UCD, and the idea was to predicting the travel time of the vehicles in a different section of the M50 using data that came from different ITS devices, such as loop detectors, and also the data that we have from the CCTV camera for journey time. And for that, we use different feature set. I mean that the feature regarding the time of the day that we want to know its travel time, the speed of vehicle, number of vehicle in each section of F50 for that we want to know its travel time. And the result was good in predicting the travel times for each 10 minutes interval. And we also tested to see how far from the current time frame we need to know about the state of, for example, travel time and waiting time. And result was showing us if we goes for 40 minutes before current travel time, we can expect that we can have a good prediction about the travel time. And also result was showing us that the number of vehicles and the time of the day has highest impact on prediction of travel time of the system. that was my start. That was the start of my work on data that comes from M50. That is the busiest motorway in Ireland, but not the last work. Currently in ROD, I'm working with different data sets that came from different sources. I mean that some of data came from ITS equipment, such as loop detector, TMV detectors, and also CCTV camera, weather stations, and data that comes from device. I mean, we also have some data that came from the incident support log, recovery logs, and also data that came from the third parties such as Waze or Google's, and also data that comes from connected vehicles such as that came from, for example, the speed of vehicle, the time that they try to stop, and also we have all data from the Motorway Operation Control Center or MOCC about the plan that they implement on M50 for reducing speed from a specific section to another sections. And data that we are handling or working with them daily is quite a lot. I mean, for example, in case of AID, we have AID loop detector in each 500 meter of M50, and it records a speed of vehicle and number of vehicle each 20 seconds of the day. So each day we have a data, and we need to process those data and figure out what's the current state of the M50, if there any specific congestion zone happen, if there any specific location for incidents happen. So dedicated software is developed for that. The one of the work that I was working on it in past few months was on if we can find any correlations between different weather conditions and possibility of collisions or possibility of congestion. Is there any meaningful relationship between the, for example, higher precipitation or higher water thickness and having more incident on M50? We use different data source, and we, as I mentioned, we use dedicated software that our team developed for showing the impact of each incident, and also in the same time the environmental conditions and weather conditions in the same time. And result was showing us from different weather parameters such as precipitations, surface water, wind speed, grid, road temperature, and similar parameters. The most important feature that we should care about them and look them to somehow find a way to apply variable speed limit is grip between the tire and road surface, and also the water thickness or surface water. And already I also working on another sort of work. I mean that, as can be expected, I also involved in project related to health monitoring of different bridges. And one of the case example that I brought here is the project that we are currently doing for Humber Bridge in UK, where there are set of sensors installed on the bridge for knowing the condition of different tire and also different span of the bridge. And our team developed a dedicated software for both knowing and showing the result in some more real-time conditions, and compressing the data to make it easier for transferring the data and also showing them on different software. Dedicated Python software is developed for also showing the result from load test on system and seeing the effect of different condition on that. If I want to somehow summarize my presentations, as I mentioned, I start my work in UCD. This question that from the different pipeline of ML model development, which one has highest impact on insight that we can have from that data or AI model. And the answer that I reached is that the link between these two is one of the critical points that we should care about that, because in most of the case we have access to high volume of data that came daily in case of ITS systems, and also we have large of data that came from SHM systems. And on the other side, we also have very well-known architecture for ML models such as ResNet or GoogleNet. So the AI models also somehow we have some good architecture for that. Maybe the main thing that we should care about that is feature engineering. And if we our results show that if we have a good feature set, the selection of ML model is less critical compared to if we just use some random features and trying to tune or ML model for different conditions. And our results also shown us that if we go with a statistical time domain features, it can be a very good starting point for different cases, and it's easy to extractable, and it can be explainable. I mean that it can give us some explanation about why ML model choose those features for its performance. In Before finishing my presentation, I once again want to thank Eleni for inviting me to here, and also this travel was funded by Royal Irish Academy as part of Charlemont Research Grant, and most of the project that I was showing was funded by Research Ireland on different projects such as Direct. And also want to thank Dr. Malik Jafarian, the head of SCA Research Group, that I had the chance to work there for around 3 years and working on different domain as I've shown you, and also Dr. Pakrashi, that I had this opportunity to collaborate with him during my time in UCD in project on wind turbine. That's all from my side. Thank you again for your presence today meetings, and I'm here to discuss about any question that you may have. Thank you.
Thank you very much for the interesting presentation, Ramin. We can open the floor for questions either here or online.
Yeah, I can start. Yeah. So Ramin, thank you very much for a very nice presentation. Because actually I have a few research topics in common with you. So I know your work is very good, and I have a few questions. The first one is, can you go back to page 16?
16.
Yeah.
Okay.
So this is a very nice laboratory test, and I worked on similar topic before. But in my experience before, for this drive by since in the roughness of the surface is always a problem.
Yeah.
So in this case, how do you eliminate this roughness?
As you can see, at least in case of this experimental setup, the surface was completely flat and there is no roughness on the model. But in finite element model, we developed some and model different roughness of the systems. And currently, as far as I know, Robs are also working with real data that came from experimental setup that was installed in the US. And in that, yeah, I know that the importance of roughness is very high because there is a lot of variation in performance of the system. At least in this case, for this setup, we didn't consider any unevenness on systems on road. But in case of finite element model, we went for different scenario of roughness, and it show us the performance may be changed, but we need to go with different set of features. I mean that in that case, frequency domain is more sensitive to type of defect and type of damage on bridge instead of, for example, time domain if we want to go for.
Okay, so thank you. So you mean like in page 19, the results they're based on simulation? It's not the
No, based on same experimental setup.
Okay. So, the accuracy is high because the surface is very like.
Yeah, maybe one of the reasons can be that.
So, do you have any results from like
Uh,
tests with higher roughness?
for finite element model, I have some result and I can show you, but I think it's in our paper. I will send those. As far as I remember, we just tested for one type of surface. As you are more aware about that than me, we can model it with different experimental idea and different mathematical equations. But the result was showing us if it goes with that finite element model, the result, as far as I remember, was around 91% accuracy for time domain. But for frequency domain was higher compared to that.
Okay, thank you. So, yeah, this is my first question. And my second question is, you mentioned for machine learning models, like feature engineering is very important. So if we choose proper features, the machine learning models don't matter. But I wonder, like, this is for machine learning, we need to do manual feature engineering, but for deep learning models, we hope the deep learning model can do like end-to-end tasks. So that means we don't need to manually extract this data. So what do you think?
Yeah, that's one of the things that we should care about. That is that when we using a deep learning model, it can do the whole procedure, but in most of the case it's some sort of black box. I mean that we cannot see what's going on, or we don't have any interpretation for features that extracted in middle of the systems. When we goes with shallow ML models, such as for example sample vector machine or cascade fit for neural network, the type of input and output is more clear, and we can see if those features that is selected are have its physical interpretations. Sometimes when we just use raw data as input of our system, the accuracy is good. I mean that in some case we can reach to very good level of accuracy. But from my perspective, it's better to know what's going on instead of the model. Sometimes we need very complicated deep learning model. That's completely true when we goes, for example, for modeling uncertainty or for the case that we want to consider a very big problem. But for a case such as, for example, damage detection of a breach, or those cases that we also need to know what's the inside the system, or the how we can interpret or ML model. I think knowing the input feature have some impact and give us some priority compared to the case that we don't know what's going on inside the models.
Okay, so based on this, can I say like compared with more complicated tasks like image or audio understanding or like large language models, like maybe our SHM problems are easier. So we don't need very complicated models. Just
Yeah, at least in most of the case, yeah. We shouldn't start with most complicated one. Let's try with simple ML model, and if you didn't reach the good result, then you can step by step make it more challenging. I mean that, for example, if in the case of transfer learning or just training a model on a specific data set and testing on another data set, we cannot rely on shallow models. We need to go with more dedicated and more challenging ML model. But if we are working on one specific scenario and the impact of response and impact of damage is more clear on acceleration response data, probably it would be better to go with ML, because then you can also explain it to someone that is not very experienced on different ML model.
Okay, thank you. Okay, and my last question is about the magnetic sensor for vehicle detection.
Yeah.
So I wonder how those sensors work. Do they detect exos?
No, they create some sort of magnetic wave. I mean that is mostly based on creating magnetic field, and when a vehicle or any things pass that magnetic field, some change happen on the variations and on the wave that is created on magnetic field, and based on the extent of and length of and type of variations, we can see some sort of pattern for different vehicles and different speeds and those things. But yeah, they just create a magnetic field, and based on that, they detecting the
So
the number of
what is the way of the deployment? You put two sensors on the two sides.
Yeah, but it depends on type of magnetic detector. For example, for loop detector, yeah, you need it's very big setup. But for case of this sensor, they just need to create two hole in row with half meter distance between sensor 1 and sensor 2, and these two create some sort of magnetic field. And if vehicle pass over that section, is count the number, and also the using some mathematical equation is calculate the speed of vehicles. My idea was to using that raw waveform as input of the model and trying to find some pattern between different vehicles and the shape of those waveform.
So I think there is one scenario, like, for example, it could be one case like there is a long truck, and another case is like two cars, but they
Yeah,
are close to each other. In this case, how does it sense?
That's the challenging part of this magnetic waveform and these magnetic sensors, that it is not a complete system. I mean that they have their pros and cons. It is easy to install, but in some case you may miss when very long vehicle passed, or when where's the head of two vehicle are very close to each other, and those are the challenge that different researchers are working on them to solve them, and with different setup to how they can improve the performance for those cases that, for example, in some case the environmental condition may also have a very impact on magnetic field that is created in using those sensors.
Okay, thank you, Mark.
Okay, thank you for your question.
I also have a couple of questions, like when we talked about like transfer learning from one network to another, and you said that this doesn't work very well, right?
For
For the identification of defects in railway.
railway, yeah.
Like what if, for example, in one railway, because you said that you had data from one specific train, what do you if you have like another train collecting data in the same network, like not transfer learning from one network to the other, what happens there?
Do you mean two train in same railway network?
Yes.
In that case, we should first of all see how far the data that we have from different set of the class. I mean that if we know that a specific section of the railway track is healthy, and we plot some a statistical representative of acceleration response data, if the data are almost in the same region of the, for example, PCA, we can somehow make sure that if we use those data as input of our algorithm, we can have good result. But if the data from the new train station is completely far from the data that we had before, and it creates another cluster, then we cannot rely on ML model that we use for training, and we may need to find some common space between the new dataset and the previous dataset. Changing each component of the systems, I mean that changing the railway track, changing the train, or changing the environmental condition has its own impact on data and on distribution of data. But the importance is that how it shifts data. It's shifted very long, or it's just close to data that we have, and we can somehow predict the condition based on the new data set.
Okay, have you tried that or?
No, the data that we had on that specific data set from Harmotech project was for whole network of France, but with one train, not in two train.
Okay.
That can be a very great idea. What would happen if we, for example, that's also one of the things, the main idea that I came here, and I also mentioned to and guys that was working in UCD and also to LNE, that we already have a good model that work on SNCF dataset. What would happen if we want to test it on data that, for example, you have from the Suez line, and to see if the data that we have from another railway network is still work, or we may need to completely change our framework.
Didn't you do it already, like in the example that you showed from another railway network?
That was, we didn't transfer between each of them.
Okay.
We used for each of them independently, and the one of the thing was that each of the data set cover a specific type of defect or maintenance.
Okay.
That one was mainly focused on, for example, tamping and surfacing. The other one was on geometrical defect. If we have two data set that covers similar type of defect, then we can go with the idea of
Okay.
transferring between one to other.
I thought that it was like the same defects like between the
No.
groups that you showed before. And for the case where you were exploring like the out of roundness like of the wheels, like the defects on wheels, where did you say that you had the sensors like on the track system?
Yeah, on track. Let me show you here. Probably this one. As you can see, the sensor was installed here in
On track and on the sleepers.
yeah, on the
And
sleeper.
how can you distinguish between like defects on the wheels with respect to those of the roughness profile? Like, you know, because you may have like defects on the tracks.
Yeah.
Because I guess the out of roundness has a specific characteristic.
Yeah, it had this very distinct sign on acceleration response data when we recorded using this sensor setup. That work was focused just on out of roundness. But if we combine that with other type of defect that came to railway systems, such as you mentioned, geometrical defect or others, that can be a very good subsequent
Because I
work.
guess it also has, like, you know, you will have some periodicity maybe, but not exactly the same, even if you have like different types of defects, even on the wheels, like, you know, local defects that not is necessarily out of roundness, or yes, then like defects on the track itself, or if it even masks the out of roundness.
Exactly. Yeah,
But you did that on numerical data, right? Not on, or do you have also experimental data?
No, that work was just on numerical model.
Okay.
Yeah.
Thank you. That's from. Do we have any other questions, or here or online?
Yeah, maybe I can ask sort of a naive question. So you mentioned, first of all, thank you very much for the very nice talk. It was very interesting. My question was that you mentioned that the features that you extract or you engineer should be good. My question is that how we can know before testing or how we can know beforehand then which features we have to extract, or if these features gonna be good or not, or gonna generalize good or not. Is there a way to guess or to know this?
Yeah, that was interesting question. Let's think about that. I think it depends on the application that you want to work on it. I mean that in case if you want to go with some general classification model that you have access to data of different class, you can test it before going for classifications and see the distribution of the features that you have. We have some sort of standard features in each domain, for time domain, for frequency domain, for time frequency domain, and we can plot, for example, the distribution of the data in each of, for example, for one of the features, and see if it show a good variation between different class of damage. That is easier when we have data from different class of damage. And for example, analysis of variance, that is one of the feature selection approach that I mentioned, is the main idea is based on the plotting the PDF of the data and check that if there is a good discrepancy between PDF of one class of damage and another, or healthy and damage. But if we want to go with unsupervised conditions that we don't have data from the damage scenario, that would be more challenging, and that was one of the questions that we was working with Mahdis and for crack detection in blade. And on that scenario, we went for some fundamental understanding about the physics of problem. For example, we says that we don't know data what would be the behavior of these features in damage conditions, but if we want to find a good features that be sensible to damage, it should have a low variation in healthy conditions. It shouldn't change very high and low amplitude during the healthy conditions, or it should have a low correlation with temperature. If the feature that we have, no matter is healthy or damage, if it has very high correlation with temperature, we cannot rely on that feature for detecting the presence of the damage or any type of defect on our systems.
Yes, exactly. I was also thinking that a physical, let's say, bound between the defect and the feature would solve the issue. Thank you
The
very much.
physical understanding about the problem. If you know what you can, what's the normal behavior of the systems, and for example, in case of the breach, you know the range of frequency for different spans based on condition of and properties of the spans, then those features or those properties can be a good starting point for the problem, and then based on the type of data that you have, you can refine and go with more detailed type of features.
Thank you very much.
Thank you.
Okay, then I guess unless we have some very quick question, we can conclude here. We're exactly on time. It seems that we do not. So thank you very much again.
Thank you.
Let's thank again the speaker for. And yes, I guess we also have the round tables now. So who takes place like in the round tables, or who wants to take place, we can stay here. Thank you all online.